Hi everyone. In this video we're going to learn about a displacement versus time graph. First of all, let us look at this. In physics, we want to observe motion, we want to record and communicate motion, we want to analyze motion. So we want to observe, we want to record, we want to communicate, we want to analyze in physics. When we observe, we use tape measures, stopwatches, cameras, and data loggers. When we record and we communicate, we use tables, graphs, vector diagrams. We might film it, use video. When we go to analyze what we've observed, we use graphs and we use calculations. So let's look at this idea of observing and recording motion, but first we need a story. Often in your tests there'll be a story. Our story is Francis got on his bike and he rode south along his street. He wanted to check the accuracy of his bike speedo. He got his older brother Benedict to time his movement as he passed chalk distance markers on the side of the road. So Francis has gotten his chalk out and he's written down the distance on the street as he moves south away from his house. He gets Benedict to time him as he rides along. He records the data in a table, and here's a table. In one column, displacement with the units in meters. In the other column, time with the units being seconds. He takes the data and he transfers it to a graph. This is a displacement time graph. We see a nice line moving upwards to the right. From the graph we can see at 5 seconds, he's 10 meters away. At 10 seconds, he's 20 meters away. It's really quite predictable, really quite regular. So this is a displacement versus time graph. And the graph itself tells us a story. From the graph, we can tell his displacement at any time during his journey. From the graph, we can determine his velocity at any time during his journey. From the graph, we can tell his displacement at any time. So how do we tell the displacement? Although our table doesn't record his displacement at 12.5 seconds, we can read it off the graph. We draw a line vertically up from the 12.5 seconds or any other time that we're interested in. And we draw that line vertically up to the line on the graph. We then draw a line horizontally from the intersected graph line to the displacement axis, and we read off the value. So at 12.5 seconds, Francis was 25 meters south from his beginning point. This is not noted in the table, but from the graph we can get this information. From the graph, we can figure out his velocity at any time during his journey. So we've got a graph here, displacement versus time, but we can actually figure out how fast he's going and which direction, his velocity, which is a vector value. And the way we do this is we look at the gradient of the graph. The graph gradient is his velocity. We find gradient by using rise over run, that equation there, and we say, okay, well, the rise, let's look at the rise. It rises 40 meters. 40 subtract 0, 40 meters. It rises 40 meters, and it runs 20 seconds. 20 subtract 0. So this tells us that his velocity is 2 meters per second. Or we should really say 2 meters a second south. Here's another example. First of all, we need a story. A jogger started out east along her regular run. She paused to tie her shoelaces, and then she carried on jogging, albeit at a slower rate. What can we get out of this graph? So we can get out of this graph, we can see that at 2 seconds, she was 4 meters down the road. So the graph tells us that story. Okay, what else can we get? Between the 3 and 5 second marks, we can see that she didn't actually move. So at 3 seconds, she stops at 6 meters east. And she remains at 6 meters east as time passes to 4 seconds and to 5 seconds. At 8 seconds, she travels a further 3 meters down the road from her shoe tying location. How do I know it was 3 meters further down the road between 5 and 8 seconds? Well, when I look at the 5 second marker on the graph, she's at 6 meters. When I look at the 8-second marker on the graph, she's at 9 meters. So 9 take 6 is 3 meters. What about the velocity? The velocity that she's running at before she ties her shoes has a gradient of 6 over 3. That's 2 meters per second in the east direction. The velocity after tying her shoes, we use the gradient, we figure that out. It's 9 subtract 6 gives us 3. 8 subtract 5 gives us 3, so it's 3 over 3. That's 1 meter per second. East is her velocity after tying her shoes. She tied her shoes between 3 and 5 seconds, which is a very, very quick tie of the shoe. She might have Velcro. We notice that the velocity before tying her shoes on the graph seems quite steep when compared to the velocity after tying the shoes. Here's another example, a news story. A family pet wanders into the garden to conduct some business. When he's finished, he returns quickly for dinner. So, the velocity on the way back, let's look at that part of the graph. Gradient equals rise over run. Now this is for the part of the graph we read at 20 seconds to 25 seconds, where the graph is sloping downwards. The graph does not rise. From 20 to 25 seconds, it doesn't rise, it actually falls. What does this mean? How do we interpret this? Remembering that up until now, we've just been talking about displacement in the west direction. Now we see that it appears that our dog is actually returning to its point of origin. So let's look at that gradient. Gradient equals rise over run. Now, the rise we see there is 0 subtract 15. So at the end of the 25 seconds, it's at 0. At the start of the 20-second mark, it's at 15. So 0 subtract 15 is our rise. It's actually a fall. Our run is 25 subtract 20, so that's 5 seconds. So looking at the gradient there, it falls. It doesn't rise at all. It falls 15 meters, where the time runs along 5 seconds. So we end up with a value or a gradient of negative 3 meters per second to the west, which can also be expressed as positive 3 meters a second to the east, because velocity is a vector and has direction. Okay, here's a final example. A walker heads north on a casual journey from his car. He pauses to smell some flowers. He turns and he wanders south. He passes his car. He keeps walking south. Where does he end up? When we look at the graph, we see that he ends up at negative 2 meters north from his car. So we see at the 12-second mark, he is negative 2 meters north. But what does this mean? It's technically true, but can we say it in a better way? Another way that we might say this is that it is at 2 meters south of his car, not negative 2 meters north, but positive 2 meters south from his car. This is a better way to say it.